Welcome to Part 4 of Module 9. The learning outcomes for the final part of Module 9 are: identify the acid-base properties of salts, and do calculations related to buffer solutions. In this part we will start with the properties of salts that originate from acids and bases. Hydrolysis is the term used for reactions in which water is split. The conjugate base for a strong acid will not react with water, and the reaction will proceed in the forward direction only. For example, HCl plus H2O gives H3O plus Cl minus. On the other hand, the conjugate base of a weak acid will react with water to produce the hydroxide ion and the weak acid. For example, C2H3O2 minus plus H2O in equilibrium with HC2H3O2 plus OH minus. The conjugate acid for a strong base will not react with water, and the reaction will proceed in the forward direction only. For example, NaOH gives Na plus OH minus. On the other hand, the conjugate acid of a weak base will react with water to produce the hydronium ion and the weak base. For example, NH4 plus H2O in equilibrium with NH3 plus H3O plus. This leads us to the question: what is the nature of an aqueous solution of a salt originated from a weak acid and a strong base? For example, sodium acetate is prepared from sodium hydroxide, which is a strong base, and acetic acid, a weak acid. When added to water, the following occurs: sodium acetate plus water in equilibrium with acetic acid plus sodium ion plus hydroxide ion. The sodium ion is a spectator ion, so the net ionic equation is the acetate ion plus water in equilibrium with acetic acid plus the hydroxide ion. There is an abundance of OH minus ions in the solution, thus the nature of the solution will be basic with a pH of greater than 7. What is the nature of an aqueous solution of a salt originating from a strong acid and a weak base? Ammonium chloride is prepared from hydrochloric acid plus ammonia. When added to water, the following occurs: ammonia chloride plus water in equilibrium with ammonia plus hydronium ion plus chloride ion. The chloride ion is a spectator ion, so the net ionic equation will be ammonium ion plus water in equilibrium with ammonia plus the hydronium ion. There is an abundance of H3O plus ions in the solution, thus the nature of the solution will be acidic with a pH of less than 7. What is the nature of an aqueous solution of a salt originating from a strong acid and a strong base? Sodium chloride is prepared from hydrochloric acid, which is a strong acid, plus sodium hydroxide, a strong base. NaOH plus HCl gives NaCl plus a proton plus a hydroxide ion. The sodium and chloride ions are spectator ions, so the net ionic equation will be OH minus plus H plus gives H2O. There is an equal amount of protons and hydroxide ions, and the solution will be neutral with a pH equal to 7. This table will help us predict the nature of a solution when a salt gets ionized. For example, will a potassium cyanide solution be acidic, basic, or neutral? It will be basic, since it is the salt of a strong base, KOH, and a weak acid, HCN. The last type is a salt that is originated from a weak acid and a weak base. For this type of salt, we cannot really predict the nature of the solution, and it depends on which part is stronger than the other. In our blood, we have a buffer system to protect the cells from changes in pH. This system is called the carbonic acid hydrogen carbonate buffer system, which is important in resisting shifts in blood pH. The chemical equation for this system is shown here. When the hydrogen ion concentration in blood increases, it reacts with hydrogen carbonate to form carbonic acid. Conversely, when the hydrogen ion concentration decreases, carbonic acid dissociates to produce hydrogen ions and hydrogen carbonate ions. The rate of this reaction is increased by the enzyme carbonic anhydrase. In tissues, carbon dioxide is converted to hydrogen carbonate ions, and the equilibrium shifts from left to right. These ions are then transported via blood plasma to the lungs. At the lungs, the equilibrium shifts from right to left, and the carbon dioxide is exhaled. This diagram shows how the cells give CO2 to the red blood cells and then receive oxygen instead. This diagram shows how the red blood cells give carbon dioxide to the lung cells and then get oxygen instead. From the previous example, we saw that a buffer solution resists changes in pH when diluted or when small amounts of acid or base are added. Buffer solutions can be made by mixing together, usually in equimolar amounts, either a weak acid with a salt containing its conjugate base, or a weak base with the salt containing its conjugate acid. The buffer capacity of the solution is the extent to which the buffer can absorb added acid or base and still maintain the pH. These acidic and basic species must not consume each other through a neutralization process. Therefore, we cannot use a strong acid with its salt because the acid will completely dissociate and will not be able to consume any more protons added to the system. Thus, we use a weak acid-base conjugate pair. For example, CH3COOH and CH3COO-, or NH4+ and NH3+. Buffers are often prepared by mixing a weak acid or a weak base with a salt of that acid or base. For example, acetic acid and sodium acetate, or ammonia and ammonium chloride. This table shows the benefit of the buffer system in resisting the pH change. In the first example, we have a water sample with no buffer, so the pH is 7. If we add 0.01 mole of HCl, the pH quickly drops to 2. Likewise, if we add 0.01 moles of sodium hydroxide, the pH will jump to 12. In the second example, we have a buffer system with a pH of 4.74. If we add 0.01 mole of HCl, the pH will drop only slightly to 4.66. If we add 0.01 mole of sodium hydroxide, the pH will only increase slightly to 4.83. Let's assume we have a buffer composed of a weak acid and its conjugate base. The equation shown represents the net chemical reaction in water. So the equilibrium constant is Ka equals proton concentration times acetate ion concentration over acetic acid concentration. We can also rearrange this equation to solve for the proton concentration. Once we calculate the proton concentration, we can then calculate the pH. Therefore, we can say that the pH value is determined by the following two factors: the value of the Ka for the acid and the ratio of the conjugate acid-base pair. When we add hydroxide ions to the buffer solution, the buffer will absorb those ions to keep the pH stable, like in the following chemical reaction. OH- plus acetic acid in equilibrium with water plus acetate ions. Likewise, when we add protons to the buffer solution, the buffer will absorb these ions to keep the pH stable. H plus acetate ions in equilibrium with acetic acid. To calculate the pH of a buffer solution, we use the Henderson-Hasselbalch equation. pH equals pKa plus log of the base divided by the acid. There are 4 variables in this equation. pH can vary depending on the concentration and type of acid and base. The pKa is equal to the negative log of the Ka. Each weak acid has a constant Ka, and therefore a pKa, and that doesn't change. Log equals logarithm, or log 10, which you'll be able to find on your calculator. Base, in square brackets, is equal to the molar concentration of the base, while the acid in square brackets is equal to the molar concentration of the acid. Let's look at an example. The Ka for acetic acid is 1.8 times 10 to the negative 5. What is the pH of a buffer prepared with 1 molar acetic acid and 1 molar sodium acetate? The first task to solve this question is to determine the acid and the conjugate base. Then you have the value of Ka, but we need to calculate the pKa to use it in the Henderson-Hasselbalch equation. The Ka is 1.8 times 10 to the negative 5. Therefore, the pKa is equal to 4.74. The log of the concentration of base over the concentration of acid, in this case, is the log of 1 over 1, which is equal to 0. Therefore, the pH is equal to 4.74 plus 0, so the pH will be 4.74. From this example, we can see that when the concentration of acid is equal to the concentration of the base, the pH is equal to the pKa. When the concentration of acid is greater than that of the base, the solution is more acidic, so the pH will be less than the pKa. When the concentration of the base is less than that of the acid, the solution is more basic, so the pH will be greater than the pKa. This is the end of Part 4 of Module 9. In the following few slides we will summarize and review the key concepts that we have covered in this module. In the first part of Module 9 we covered reverse reactions and introduced the concept of chemical equilibrium. From the graph you can see that the rate of the forward reaction is at top speed at the start of the reaction. The rate drops as time goes on, and the reverse reaction is at its lowest speed at the start, and the rate will increase as time goes on. At one point the rate of both reactions becomes equal. This point is called the equilibrium. In the second part of Module 9 we investigated Le Chatelier's principle and the impact of certain stresses on the chemical equilibrium. The first factor we introduced was the effect of concentration. The following table summarizes the changes associated with different changes of the concentrations. After that, we looked at the effect of volume on the chemical equilibrium. It is very important to remember that only gaseous matter is affected by changes in the volume. The effect of volume is directly related to pressure, so an increase in volume causes a decrease in pressure, and vice versa. The third factor from Le Chatelier's principle is the temperature. We consider heat as a reactant in endothermic reactions and as a product in exothermic reactions. The final factor is the catalyst. We explained why it does not shift the equilibrium, but it makes the rates of both reactions faster. In Part 3 of Module 9, we covered the equilibrium constant expression. For example, the KEQ for this reaction is expressed as such. The stoichiometric coefficient in the equation is reflected as the power in the expression. For instance, the 2 for ammonia and the 3 for hydrogen. The second constant we covered was Kw, the ion product constant for water. This is equal to the molar concentration of hydronium ions times the molar concentration of hydroxide ions, and it is always equal to the value of 1 times 10 to the negative 14 at 25 degrees Celsius. The last constant we discussed was the acid ionization constant, or Ka. For example, the Ka for the acetic acid ionization is equal to the following equation. Remember that we don't include the concentration of the solvent in this expression, as the changes in its concentration will be negligible. Ka for acetic acid is equal to 1.8 times 10 to the negative 5. Every weak acid has a different Ka. In the last part of Module 9, we covered the acid-base nature of salts. We explained that the origin of the salt plays a critical role in determining the nature of the solution. For example, a salt that comes from a weak base and a strong acid will produce a solution with an acidic nature. The final topic we covered was the buffer system. We discussed the hydrogen carbonate carbonic acid buffer system and explained how it protects our blood from pH changes. We finished this part by looking at the Henderson-Hasselbalch equation that we can use to calculate the pH of a buffer solution. This is the end of Module 9. Please practice the weekly exercises in your textbook and the questions you find in the workbook. We will meet face-to-face in the tutorial sessions, and this will be your chance to ask any questions or seek further clarification.